If polynomials are the integers of the algebra world, then we need to be able to take the integers of the algebra world and make algebra fractions. And that's what we've got going on here. We can take any polynomial, put it over top of any other polynomial, and say, all right, cool, algebra fraction, aka rational expression. As it turns out, those rational expressions correspond to rational functions. So you've got a rational function if you have any polynomial function over any other polynomial function. The most basic, so we can add to our list of basic graphs, basic functions. We've got f of x equals x squared, x cubed, square root of x, cube root of x, absolute value of x, 1 over x. There are some distinctive features here to take note of. Because that denominator could be 0, which we know is a no-no, there's something happening where x is equal to 0 or near x is equal to 0. We would say that our graph is going to approach that value, and graphically we could say that's a vertical line. So the graph is going to approach that vertical line. And from each side, it approaches in a different way. Also, though, the farther to the left and the farther to the right that we go, we also have our graph approaching a different line now. This one is a horizontal line. So can we take this kind of behavior and expand it to other kinds of rational functions? Will we always have that sort of end behavior where we approach a horizontal line? Are there always going to be these vertical lines that we approach? How do we know? What's the scoop? So let's take a look at these things, starting with the one that is the first distinctive feature mentioned for our basic function, f of x equals 1 over x. We would call this a vertical asymptote because we've got a vertical line, vertical, and asymptote referring to something that we approach. So we've got our graph approaching, and as it happens in this particular case, we will not cross. So we will not pass across, we skip over. We skip over a vertical asymptote. So we can have stuff on either side, but we will never have with our functions something smack on top of those vertical asymptotes. We are not going to cross over those. With the rational functions, what we're going to do is we're going to take that denominator and set it equal to 0 and solve for x. Now, we say we're usually going to do this because there is something else that can be in play that we would need to watch out for. And so we'll come back to this. But the basic idea, hey, if we're taking something, setting it equal to 0 and solving, as long as we can solve that kind of equation, we're in good shape. So for instance, in this example, find the vertical asymptotes for the function g of x equals x plus 1 over x squared minus 9. We're going to take that denominator, set it equal to 0. We can use the square root method very quickly. Add 9 on both sides, do the square root of both sides, remembering our plus or minus, getting those two different x values, x equals 3, x equals negative 3. Now before, we had that good kind of habit of saying x equals, x equals. Now this pays off in a much more practical way. Not only have we been clear about communicating our solutions, now we get to say that kind of habit now makes it all that much easier for us to report those vertical asymptotes, because we will always correctly report a vertical line if we are always saying x equals a number. So we've got that habit now working in our favor here as an extra layer to that kind of, well, requirement of saying x equals. So we've got those vertical lines, x equals 3, x equals negative 3. If we were taking a look at a graph, and we could get our graphing calculator to help us out with this, our graph on the left side of x equals -3 would approach that vertical line somehow or another. Either it would approach it, come in, and shoot upward, or it would approach it coming in and shoot downward. In between the x equals -3 and the x equals 3, all different kinds of stuff could be going on, but as we got close to the x equals -3, we would be coming in, shooting up, or shooting down. Go over to the x equals +3, shooting up, or going down, one of those two. On the other side of the x equals 3, on the right-hand side, coming over on the right-hand side, shooting up, going down. Be one of those two possibilities on each left and right side of those vertical lines. But we just needed to find them, so we found them. We can worry about how that'll fit in with other stuff later. Remember, we've got a lot of different variation for what we could encounter. So vertical asymptotes, take your denominator, set it equal to 0. In this case, hey, 4 terms. We could try factoring by grouping. Group the first pair, group the second pair, factor the first pair, factor the second pair, get that same 9x minus 1. Hey, I've got an x squared minus 4. My factoring checklist can help me remember that I can factor that sucker using a difference of squares, get me an x equals 1/9, an x equals -2, and an x equals +2. We know from our polynomial stuff we should expect that we get 3 zeros, 3 solutions to that. So we've got a lot of that stuff kind of wrapping together. Hey, yep. So we're expecting 3 of those vertical asymptotes, because again, we haven't thrown a wrench into the works yet. We're saving that for a little bit later. For our basic function, we have what we would call a horizontal asymptote. So that would be a horizontal line. This is something that our graph will approach to the far left and or. So sometimes it might be just to the far left. Sometimes it might be just to the far right. For rational functions, we get a little bit of both. So for the rational, we get the and, not the or. For other kinds of functions that we might encounter, we might have a horizontal asymptote, and it might be just approaching to the far right. It might be just approaching to the far left. It doesn't have to be both, so we made our definition as generic as possible. For our rational functions, it's going to be both far left and far right. We're approaching some horizontal line. We could be approaching it from above. We could be approaching it from below. We just don't necessarily know. Could we figure it out? Maybe. We'll see. These horizontal asymptotes can pop up in 2 different ways, and that is based on how our numerator and denominator are related to one another. If, like our basic function 1/x, the degree of the top is smaller than the degree of the bottom, then our horizontal asymptote is going to be that same y equals 0 that we saw earlier. But if the degree of the top and the degree of the bottom are the same, then we have to use the leading coefficients of the top and the bottom to come up with that horizontal line instead. So this is quick enough to show a couple of different variations. Here's that original function that we were looking at before. The g of x equals x plus 1 over x squared minus 9. The degree of the top is 1. The degree of the bottom is 2. The degree of the top is small. So that has a horizontal asymptote y equals 0. It's automatic. Boom. There it is. How about that function h of x that we were looking at a couple minutes ago, worried about the vertical asymptotes, where we've got a cubic on top, a cubic on the bottom. The degree of the top is the same as the degree of the bottom. Well, we've got to use those leading coefficients. The leading coefficient from the numerator is the 3. The leading coefficient from the denominator is a 9, so y equals 3/9. But we can simplify that So the final answer, y equals 1 over 3, would be that horizontal asymptote. What we're missing from this set of relationships is, what if the degree of the top is bigger than the degree of the bottom? So what happens then? Well, that brings in some of our division business. And what could happen is that we would get something that we refer to as a non-horizontal asymptote. There are, again, different ways that things could interact, and things could be very, very strange. But what we end up looking at is, if the degree of the top is only 1 higher than the degree of the bottom, then what we would get is some sort of slanted line. So it's not vertical, it's not horizontal, it's some line with a slant to it. And we could then refer to that as a slant asymptote, or if we wanted to be a little fancier sounding, an oblique asymptote. We would need to use either long division or synthetic division. Synthetic division is a sometimes thing. So this doesn't always work. We may occasionally have to resort to long division to work out a non-horizontal asymptote. And again, we are just going to now worry about the slant or oblique asymptote. So for x squared minus 1 over 2x minus 4, the top has a degree that is 1 higher than the bottom, degree 2 versus degree 1. We are going to get some sort of linear expression that we can then turn into a linear equation, a linear function, as our slant, aka oblique asymptote. I'm going to show you a little cleverness about a synthetic division, like what's happening here in this example, just so that you have a little bit of extra algebra power in your toolbox if you want that. We can use synthetic division because the denominator is linear, but we can't use it immediately because that denominator does not have the form x minus a number or x plus a number. The 2 out in front is throwing things off a little bit. So here's the cleverness. Let's take that 2 and factor it out. If we take that 2 and factor it out, we're going to save it. We're going to save it for out in front of our denominator. We're just going to take that 2 and save it. That means that we can really focus in on this x minus 2. So for the synthetic division that we've got to work out, our coefficients from up on top, 1 for the x squared, 0 because there is no x term, and then the minus 1. X minus what number? Well, okay, so that's a 2. Again, we could also say whatever is after the x, change the sign. So negative 2, change the sign, get a positive 2. Run through that synthetic division. The 1 drops down. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 1 plus 4 is 3. We're not worried about that remainder, though. We're worried about the quotient. And the quotient, 2 is the constant. 1 is for the x. So the quotient is the x plus 2. And that would mean that this slant asymptote, aka oblique asymptote, is going to be based on that x plus 2. But remember that there was also that pink 2 that we had down in the denominator that we were saving for later. Now is the later where we've got to bring that back in. If that x plus 2 is the quotient and the 2 is still hanging out down on the bottom, then really what we're looking at is this 1/2 x plus 1. Slap a y equals out in front, there's your oblique asymptote. If you were not interested in trying to cleverly use your synthetic division, you would have to do your long division. Your long division is still going to get you that same result. We ignore the remainder. We only worry about the quotient. Y equals the quotient is going to give us that oblique asymptote. So here is that sneaky part that I had mentioned earlier about coming into play with our vertical asymptotes. There is this possibility, as we're looking at things being tied in with denominators and numerators, if there's a factor that is the same between the numerator and the denominator, a common factor between the top and the bottom, then that's going to correspond to a whole. That whole would not be tied to a vertical asymptote. It would be a whole. That whole is not going to play any sort of role in us finding the horizontal asymptote. It's not going to play a role in us finding the oblique asymptote either, because again, it's a common factor between the top and the bottom. It's something that we can eliminate as long as we recognize, hey, while I'm going to eliminate this, I am going to comment that there's a whole. So in this particular example, when we factor that numerator and denominator and we see this x plus 1 common to the top and the bottom, what's happening here is that these original function and this reduced function are exactly the same, except there is a hole in the graph at the x equals -1. So whatever the y value is, which we could try to crank out, right? The y value, -1 minus 3 is -4. -1 minus 5 is, or excuse me, -1 minus 4 is -5. So negative over negative is a positive. The y value when x is equal to -1 would be a 4/5. That's where our hole is. Our hole at x equals -1 would actually be showing up at the point -1, comma, 4/5. Every other point on this graph and this graph, identical. Every other vertical asymptote, every other horizontal asymptote, because this one's degree of the top 2, degree of the bottom 2, that's got a horizontal asymptote. We're going to be aware of those holes. We're going to worry about holes if they ask us anything about vertical asymptotes, going backwards to older stuff, intercepts, and going back even farther to stuff that we don't necessarily always rely on but could still be asked about, domain. We want to worry about finding holes with any of those sorts of things to make sure that we are not incorrectly trying to report something that is a vertical asymptote. No, that's a hole. We're not trying to say, oh, hey, snap, I was looking for some intercepts, but oops, a hole found its way in there. Or, well, we always got to worry about those sorts of things when it comes to the domain. Anytime that the denominator is equal to 0, we want to make sure that we would find the domain before we reduce out any of those common factors on the top and on the bottom. We got to find the domain first. Before we reduce things out, find the domain. Make note of any holes before you find intercepts. Make note of any holes before you find any vertical asymptotes. So, bringing it all together, what if we are just simply tasked with finding all the characteristics of a rational function? That means that we would be interested in, starting with the basics, domain, y-intercept, x-intercept. We got to worry about holes, vertical asymptotes, got to worry about holes, And there's that possibility of either horizontal asymptotes or slant asymptotes, aka oblique asymptotes. So we're going to worry about those as well. Whichever one pops up is what pops up, and we find it based on what we've known. So if we are worried about those sorts of things, let's take them in that order, because those holes kind of mess stuff up. So we don't necessarily go, oh, what's the easiest thing to do? What's the quickest thing to do? It's better to take them in order, be safe, make sure that the holes don't screw something up along the way and catch us off guard. Fact at the top, fact at the bottom. There are no common factors on the top or on the bottom, so that means that there are no holes in this particular case. So thankfully, we've got that issue dealt with. Domain is going to be tied in with our vertical asymptotes. So we can go ahead and link those two together. We still have them listed separately, but we could go and fill this in. As soon as we've got the domain handled, we could go and say, all right, let's slap in the business about vertical asymptotes, and those are both handled. We don't want our denominator to equal 0. We don't want x to equal -1. We don't want x to equal 3/2. So we pop those out from our number line, and we have our interval notation version of that domain. We could then immediately pop over down into our item 4 and say, what's going on with item 4? Well, that's already done with the domain. Let's just go ahead and jot down that x equals 3/2, the x equals -1. Boom, that's done. Y-intercept. Plug in a 0 on the top, on the bottom, simplify. There you go. X-intercepts, take the top, set it equal to 0. That's what we got to worry about. A fraction equals 0. The thing that we've got to worry about is if the top is equal to 0, because we've already taken care of the issue of holes. Holes aren't going to screw anything up, aren't going to lead us astray. We've already realized what's going on about holes, so we can now say, all right, take that numerator, set it equal to 0. That factors. We already factored it. Boom. Solve. X equals 4, x equals -2, therefore 4, 0, -2, 0. Leaving us with the horizontal asymptote. Degree of the top, degree of the bottom are the same. So we come back to that original function. Leading coefficient on the top is 1. Leading coefficient on the bottom is a 2. Therefore y equals, don't forget the y equals 1/2. There's our horizontal asymptote showing up. If we needed to graph, like sketching things by hand, we could take this stuff, we could put it together on a grid, and then we can start trying to, with critical thinking, piece together how are things going to look as we approach those vertical asymptotes. How are things going to look when we approach that horizontal asymptote off to the left, off to the right? We would say, how are things going to have to link up based on the appearance of our x-intercepts and y-intercepts? Can we use those to help us figure out how things are moving, going up, going down? What's the scoop? We also, again, have our graphing calculator, so we could, as long as we're allowed, just use the tools that are at our disposal to do that. And, hey, good for us. But these are the things, and plenty of this stuff is stuff that we would not be able to pick off of a graph that's generated by our calculator. 0,8/3. That's not going to be something we can identify by eye. Possibly the x equals 3/2, but we might have to go digging a little bit before we actually can be sure that it's x equals 3/2 as opposed to something that's close by. There are always those things that we've got to worry about, limitations on our graphing calculator or other technology, even limitations on the algebra methods that we know and have to use. So we want to make sure that we know what we can know and can use what we have at our disposal. Sometimes that does include other things like technology. Sometimes the technology does not necessarily help us. So things to keep in mind. But here we've got all of that stuff being put together.